All right, welcome back. I'm Captain Paul Weskelnies. I'm one of the mechanical instructors here, and I will be your last lesson for the day. So we're going to be going over unit price mechanical, as you can see here behind me. So we'll be going over, I'm focusing mostly on quantity takeoffs. So let's identify the parts in the system. You've had a lot of time looking through RS means, reading through the tables and doing math. I'm going to stay away from the math because we've got a lot of systems to go over and a lot of components to talk about on how it's set up and things that you're going to want to look for to make sure you get accurate unit price estimates of your mechanical designs. So without any more talk, let's move on. So my goal is that you understand how to estimate the quantity and cost for building HVAC components. That's it. We're going to go through and identify them and then talk about some of the labor, how that's adjusted for what you're putting in, some of those labor-only items, and then how you would calculate the cost for certain things. So first thing to do when you get your design is to look through the plans. Try to figure out what are you doing? What is the goal of this mechanical system? So we're focusing on HVAC. You could also start talking about plumbing, fire suppression, but we start going down, and it took me a long time last time to cover all those. So we're going to focus on HVAC. So look at your HVAC drawings. What are you trying to do? Where is your environment? What is the goal of your system? So special requirements, if you're doing a hospital, operating rooms have special requirements, outdoor air requirements. Are you just a regular office building? Well, even those have requirements, but those are a little more generalized. So try to find, is there anything special about this? What is the overall design intent? What is your heat source or your heat sink on here? Identify any kind of discrepancies between them. If you're calling for a 100% outside air system and you have return vents going back to the air handler, you have a discrepancy. So make sure you know what's going on with your system first. And then look at the structure, the site layout, and how these other things that will affect your mechanical systems. Mechanical ends up being one of the last things you put in design, and you don't want to run a duct right through a structural column. Go out there, determine where your HVAC systems are running. So first thing, do the quantity takeoff. Make a list of the types of materials that you have in there. The good thing about mechanical system is there's going to be a lot of repeat of materials. So if you're running through one run and you've already identified certain things like variable air volume boxes, certain kind of valves, balancing valves, and you've found those in one section of the system, you're probably going to find them a little bit later in the system as well. There's a lot of common components that you can identify. So make sure you keep finding those on your, as you're going through and looking for them. If you found isolation valves at one point in the system and you haven't counted them for another part, go back and see if you can find isolation valves on there. Apologize for this. I may just start throwing HVAC terms out there, and if you're a civil person and you're like, I know HVAC exists, bear with me. I'll show you where they are on the system in a little bit. You can always look through your drawings, and hopefully your design contractor has actually gone through and labeled them properly. So go through the system, and not just one system. The HVAC system can be broken down into heating, cooling, water distribution, air distribution. So start at each individual system. Don't try to go through and tackle it all at one time. You'll probably miss something when you do that. Go through, look at your systems. Do we have a heating water loop? Do we have a cooling water loop? Are we using mostly air distribution? Find those systems and start with one of them and go through there. And don't forget the labor-only items. So this is the first time I'm going to say this, and I will say this at the end again, because don't forget about labor-only items. A lot of times my experience is testing and balancing is at the very end, and we're already behind schedule, so we need to turn over this building to the user because they're bugging you, the wing commander's bugging you. So you don't properly allow for some of those things to make your system work. It's kind of like eating a cake. You go to the store and you buy a cake, but you want the cake now, so you can't put the icing on there. Will the system work? Yes, it meets the intent of being a baked cake, but it doesn't taste very good. No frosting. Nobody really wants that. So don't forget about these items that will possibly happen at the end. So the order that I recommend going through this is consider your source, then the distribution and the use. So the use being the room that I'm in, I require cooling. So I need air in here to maintain humidity and temperature conditions. From a design perspective, we typically consider the use first. When you're doing your cost estimating, if you can start at the source, you can learn a lot about the system. How are you distributing this? Where are you getting your cooling from? Where are you getting your heating from? And then you can connect the two with distribution. As you're going through, you can start with the HVAC equipment. So at your source, start with the big equipment. So your chillers, your package units. If you start with those are going to be a significant portion of your cost. Weight and size may be important. For example, here at AFIT, our chiller is located on the roof. It is a very big piece of equipment, and we have to raise it 3 stories. So you can't necessarily just bring it up piece by piece through the stairwell. So you'll have to hoist it onto the roof. A lot of your rooftop units, package units, well, those need to get up there somehow as well. Your sheet metal. For rectangular ducts, a lot of that is calculated by weight, which makes it a little bit more complicated because you have to account for how much ductwork in area and then determine the weight based off of the density, based on the dimensions of your ductwork. So we'll start with the primary equipment, your source, and then move towards the use. So I believe you've seen this drawing before a few times. This is your example EOD building, and already highlighted on here is your distribution system. I believe you have a homework question on this part right here. I'm not talking about that in here, but we're going to talk about the procedures to go through this. So the source for this building is, I'm calling it a heat sink. Your air-cooled chiller. It's an air-cooled chiller because it's labeled such on your drawings. Don't try to guess what it is just looking at it, because this could be a few different things looking at it from the top. But it's an air-cooled chiller. This is where you're rejecting your heat from. We then have a mechanical room, which is connected to your heat sink through a water system, a chilled water system. Side of your mechanical room is your air handler, where we bring outdoor air into the air handler, and we treat it, we condition it, we heat it, cool it, dehumidify it at the air handler before sending it on its happy way out to the zones. So this is our supply air. So what's leaving the air handler out to be used by the zones, which are being slowly highlighted in blue, we'll be referring to that as supply air. And those are then sent out to the zones, and we have diffusers at the very end of the runs. And this is where the air is mixed into the zone, and this is what you feel as an occupant of the zone. The other air that we will refer to are the return diffusers down over here. They're spread out through each zone because when we push air from the outside in and we condition it, if we don't let it escape, we're going to pressurize our building. You know when a building's been overpressurized when you go and you open a door and it flies open really, really fast. The building's probably pressurized. One example that I've seen that one of my buddies at IMSC sent me was was a building, I think it was actually at Kirtland, I think we might have some people out at Kirtland, where the roof was basically inflated like a balloon, and the guess being was because it wasn't balanced between the outside air and the return air. So they pressurized it. The roof membrane wasn't constrained with rocks on top of it, so it ballooned, it inflated. We typically don't like our roofs to inflate unless it's one of those football training centers, so hopefully that was accounted for in your design and your startup. So we have return diffusers. In this case, this is a plenum return, so we pull the air up into above the ceiling tiles, And then we have grates between the walls that allow air to flow out to our relief air louver over here and then out of the building. So those will be pushed out by your air handler supply fan through the whole process. So our sources. The whole thing about HVAC is actually very, very simple in intent. It gets a little complicated, but it's very simple. All we're doing is moving thermal energy. That's it. So in order to do this, we need some kind of heat source. So in the winter, it's cold outside. Energy moves from a hot environment to a cold environment. It's like gravity. Something will fall from a high elevation down to a lower elevation. So heat moves the same way. It's going to move from high energy, high temperature to cold, low energy air. So we need to have a heat source in the winter where we start a fire and we basically add heat back into the building to replace the losses through the walls out to the environment. In the summer, we have the opposite effect. It's nice and cool in here if your HVAC's working. It's nice and cool inside, and heat's going to come in from the outside. So we need to pull that heat out. Somehow we have to pull that heat out. So this is what our cooling equipment does, our heat sink. And we move heat through 3 different mediums. We have air, which we're very familiar with. Chances are you look up onto your ceiling and you will have a supply diffuser somewhere above you, or you'll feel the air moving. We move it through water as well, which typically you won't see on a regular basis because that's in pipes hidden on the walls and above you in the plenum space. And then we move it through refrigerant. You're probably familiar with this at home if you have your typical split unit at home, your condensing unit outside. Refrigerant, we move refrigerant through using you can see over here, our lines running refrigerant from the outside condensing unit to the inside to which we generally refer to as the furnace or your air handler inside your house. So over my shoulder here, you have your typical boiler where we burn something, be it coal like at Wright-Patterson at a central plant, natural gas, or it could be electric resistive heater. We provide this heat, we mix it around water in this boiler, and we distribute this water out to our air handlers, out to our variable air volume boxes with reheat coils, whatever use we need to use it for. And then over here, we have our water-cooled chiller. And this basically uses water we have a chilled water loop inside your building where we circulate that through your air handler. We then reject the heat from the water into another water system, and we reject the water outside through a cooling tower or a water tower. So in all of these systems for cooling, we have to move the heat outside. Your condensing unit, you're going to move it outside through refrigerant and reject it to the air. Your cooling tower, you're going to reject to the air through evaporation by pouring water over coils and running air across it. As you can see, there's fans over here that blow water or blow air through the water, cause evaporation, and decrease the temperature of the water. And the middle step with our cooling tower is our water-cooled chiller. So our cooling sources. So I told you earlier, we have our air-cooled chiller up over here, which the purpose of the chiller is to create chilled water. Water is typically going to be between 35 degrees to 45 degrees to provide cooling. Our air-cooled chiller supplies chilled water. This goes to our cooling coils in our air handler. That's the only place where we dehumidify, where we cool the air, is at the air handler. So options that you could run into with your primary equipment. For this, it is an air-cooled chiller, which means it must be placed outside. We need to have plenty of airflow to be able to reject the heat, much like your condensing unit. Wherever you're going to reject the heat, it's going to be outside of your building. If you have water-cooled, you will place that inside of your mechanical room. But you must have something outside again. Your water tower, your cooling tower will be placed outside. And then you'll have different compressor types: centrifugal, reciprocating, scroll, rotary screw. So looking at this drawing set, I can't tell you what this is. You're going to have to find that. If you're the mechanical engineer doing the design, you're going to be speccing that out yourself, or you're going to have to go through. If the contractor hasn't told you what type they want to put in here, reach out to them, ask them that question, or it will be listed in a schedule somewhere. So you'll have to find that and size it off of there. And then lastly, probably the most important thing once you've identified what kind of equipment is what size of equipment. And so we size this off of cooling tons. Now this cooling ton is not 2,000 pounds. This is in BTUs per hour. This is energy transfer rate, represented by traditionally the amount of cooling 1 ton of ice, 2,000 pounds of ice, would provide over a 24-hour period. So here is what it looks like in RS means. And the question that I have for you is, what is 1 ton? Well, 1 ton, as we refer to as a cooling ton, is 12,000 BTUs per hour. So there's your conversion factor. We only refer to tons when it comes to cooling. So you'll never refer to a heating ton, because that doesn't make sense. Your mechanical engineers, your HVAC technicians will possibly laugh at you. But 1 cooling ton is only used for cooling, and that represents 12,000 BTUs per hour. So you go into here and you can look at the drawing, and you can see that it says reciprocating type chillers with standard controls, water chiller. So with standard controls, you can get fancy with them, but they have on here water chiller, integral air-cooled condenser. So this is your air-cooled chiller, in that the condenser, the part that we reject the heat from the refrigerant, is going to be cooled with air. Your water cooled? Well, it's cooled with water and a cooling tower. And then you have your sizes on here. So you can see on here the 60 ton, 70 ton, 80 ton, those are your cooling tons, not referring to the weight of the piece of equipment. So you can run through RS means, and they have many different types on there. You can choose whether that's the reciprocating, centrifugal type compressor, and then size it based off of the specs. What does it say in your schedules? Is this a 60 ton? Or if they give it to you in BTUs per hour, convert it to cooling tons. So now that we have the water, it's been chilled, we have to move it to where we want to use it. So we use water in a lot of cases because water is much better for moving thermal energy than air. We like air. Traditionally, we like air because air is very useful. In the end, in your zones, we treat the air. We do air conditioning. We don't do water conditioning. We do air conditioning. So we like to distribute to the zones air because then we can mix it, and that's what you and I feel. But we can move water to and from the sources to the use because it's more efficient to move the same amount of thermal energy. As a duct this big, we need a pipe maybe yo big. So yo is an official measurement. I think you can Google it and find out about how big that is. But we can move more energy at a lower volume, and pipes are much easier to run than your ductwork. So higher heat carrying capacity at a lower volume. So high specific heat, high density. So the sizing of this, doing the quantity takeoffs, wouldn't be so difficult from plumbing. So the same process will hold true if you're then translate to your plumbing set, except HVAC is more complicated. We have more types of valves in there. We have control valves, we have balancing valves, we have all sorts of valves in there. And the other thing that makes it different than plumbing is we have a closed loop system, meaning we take the water at the source, we take the water, we treat it, we send our supply water out to be used. In a plumbing system, that use will be at like a lavatory. And that lavatory, you turn it on, and the water falls into the sink or into the drain. And then we get rid of it. And that would be an open loop system. With our HVAC and our heating and cooling water, you will use the water, and then you will return it right back to the source to be treated again. The water will stay in the system. So you have a looped system. There are some systems out there used in the past for like cooling, where rather than returning the water back, they would use it and then discard it, because figured it'd be more energy efficient if we just treated colder domestic water or colder groundwater, cooled it a little bit more, and then once it warmed up, we just get rid of it. However, that is not water efficient. If you're in a place that has a lot of water, it could be more efficient for you, but I believe by UFC, it is not condoned. If you're in Phoenix, water is extremely valuable. That is not a very good option for you. So you can see behind me a diagram. This is taken from this building of all the different valves. It's a piping diagram, and it shows all the types of valves that are on here. And I've called out a few of them. We have the control valve. We have heating valves way over here. We have other equipment in here. We have an expansion tank. We have an air separator. We have our heat exchanger heat source. We have backflow preventer. And we have all sorts of things that if I were to label them all on this drawing, you would just see labels. So find a diagram like this when you're doing your quantity takeoffs. What we're going to look at is a little bit more simplified using the EOD drawing set, but you want to have something more comprehensive than what I'm about to show you. So our chilled water system for the EOD set, we have our heat source located over here. There's our air-cooled chiller, and we have a run from which we bring water into our mechanical room and down to our air handler. So if we're going to do this quantity takeoff, you can measure using a scale your piping. And there's also a label right here that has the size of the pipe. So you're going to go and it's going to be 2.5-inch chilled water supply, CHS, chilled water supply. Consult your glossary, your key on what the labels mean. But 2.5 inches, that's the size of your pipe. So you can measure that. The good thing with this is simple. It's 2.5 inches all the way around this system. So going to the air handler, we don't really have much splitting off on here, so it's 2.5 inches all the way around. But don't forget, you can see that there's a single line running here. At this point, I can tell you that there's both a supply and a return here. So you have to account for both of those, even if it's not shown on there. The other thing you want to find, you should find, is some kind of elevations. What is your riser diagram? What is the vertical? So these will probably be coming, at least my experience here at AFIT, is these will come in above my height at the ceiling level. They'll come in, then they'll drop down to the air handler and enter the air handler about here. So you'll have a vertical run in there as well. And then you're going to have your fittings. You're going to have a 90-degree bend in there. You're going to have other things such as T's over at this point. So account for your fittings. And you're going to come across various valves. So you have an isolation valve right here. When designing this, hopefully your mechanical engineer has put in isolation valves on either side of your pieces of equipment. This allows us to do maintenance without taking down the entire system. So we have our isolation valve. We then have a balancing valve in here. All of your systems, for this system, it may not be as critical to have a balancing valve as we only have one air handler on here. But when you start talking about your multi-zone, multi-air handler systems, your more complicated systems, you are definitely going to have balancing valves around here. Also to be included with your balancing valves, don't forget the labor-only item, in that later you're going to have to do testing and balancing of this system. So for each balancing valve, you're going to have to add in testing and balancing to your estimate. We'll then have a control valve right here, which will then control how much water flows into our cooling coil. So the control valve, there'll be different flavors of it, but you'll also have an actuator involved in, you're going to have some kind of actuator, some kind of control system connected to it as well. So that will be measured. What will be controlling this valve is if the air temperature after the cooling coil decreases below the set point, that control valve is going to allow more chilled water to flow in and reach that set point. So we have our control valves. We then have isolation valves on the other side of our cooling coil, so we can be able to pull out that cooling coil and do maintenance as necessary without having to drain the whole system. We'll then have an air separator to remove air from the system. We'll have an expansion tank in there to maintain consistent pressure within the system to absorb some of those changes of pumps turning on, valves opening and closing, without absorbing that inside of your, without absorbing that at the fittings and at the connections. We then can come over to a T where we're running 2 pumps in parallel. This allows us to run, turn one on and turn the other off, possibly remove it, replace it as necessary. Or they could be sized to run together and then you double your flow through the system, roughly double your flow through the system. Once again, we have isolation valves. I love these things. We have a strainer on here. So the strainers will be used to help pull gunk out of the water before it gets to certain things. You'll have things that you like to protect, your pumps and your cooling coil. Your cooling coils can get gunked up very easily if you don't have strainers in the system, depending on your quality of water that you have running through there. So you have your pump, 2 of them, and at the other end you'll have a check valve. The check valve will prevent water from flowing back into the pump. If, say, the top pump is off and the bottom pump is running, water may want to flow backwards through the pump, which isn't good for the pump. So you'll have a check valve to prevent flow from going the wrong way. You'll have an isolation valve there to be able to isolate it, pull it out for the same reasons, and then a balancing valve to balance between the 2 pumps to make sure that there's the same consistent pressure drop between them. Or you could have a triple duty valve, which does all 3 things. By UFC also, these are not recommended because if you were to use this as both a balancing and isolation, you turn that valve completely off, well, you'd have to open it back up to its balancing point. So if you don't do that, it's going to be off balance very quickly. So if you don't know what these items are, consult the schedules. They should give you the specifications for them in there. So here's a table, bit of an eye chart to read. But what I have on here are each of these items. So you can look over here and you see pipe, 2.5-inch diameter. On this far side over here, this number would be the reference to your RS means. Where am I pulling this from? And we measure this in linear feet. So how do you get this? We're going to have to measure it off the drawings. So you're going to need a complete set of drawings to be able to measure this off and estimate it. Notes that you have on here, it's Schedule 80, threaded with couplings and clevis hanger assemblies. So go through, read how thick is the pipe, what size is the pipe, what material is the pipe, is it copper, is it steel, is it iron, is it PVC? All different things that would go into choosing this pipe. Then over beneath it, you have your steel fittings, 2.5-inch diameters. Once again, you're going to count each of these in there. And they have considerations. They can be flanged, they can be welded, they can be threaded, they can be, you name it. So go through and make sure you've read each of these. So your flanged will probably be easier for maintenance. Your welded, or easier from a labor cost perspective. Welded will probably be a little bit more expensive. Then you have your air control. So read off the schedules of what it is. So air separator with strainer, isolation valve, and your control valves. I did not include numbers on these because as I was going through them, I realized that there are many different flavors of this. So consult your schedules, find out what's in there, what they are. So your isolation valves, you're going to have multiple of these. Your control valves, you're going to have one for each system you need to control. So each cooling coil. so on and so forth. And you're going to go through and you're going to count each. With your control valves, there's probably going to be an actuator involved with it, so you're going to have to count for that as well. And then testing and balancing. There's going to be another line item for testing and balancing, and that's in a different section. Last few things, we have the pumps, 2.5 inches with a 1/4 horsepower. You're going to count each of those again, and each of these will be determined based off of the type of the materials, the impeller, also the materials of the impeller, and what kind of connection. So the example I have on here is this could be a cast iron case with a bronze impeller and a flange connection, and there'll be a line item for that. Apologize, we're not talking, I may be talking a little more into the design of this, but the good thing is everything that I'm saying here will be labeled on your drawing sets. If it's not, consult your engineer, consult the person who did the design, because I'm not expecting anybody to be full up mechanical engineers except for your mechanical engineer. But all of this is drawn on there, so you don't have to guess. Like if they don't put an isolation valve on there, well, I'm kind of putting your bug in the back of your mind that, oh, Captain Westley said something about isolation valves. But if they don't include it, unless you're the mechanical engineer, you're not going to be the one to catch it. Just go on there and count the valves. Just count each little step on there and just build a list. And if there isn't a diagram on there, a note saying what this is, talk to them. So then expansion tanks, also sized based off of their gallon capacity. Sized on the material and the capacity of them, which again will be provided to you. Or if you're the design engineer, you'll know how to calculate that. So, and then the last thing that I have not talked about is you have insulation here. And that's going to be measured in linear feet. Now there are many flavors of insulation as well. Cotton candy is very popular for your housing, but there's also other types for your pipes. And you'll want to wrap this around, especially on your chilled water systems, because chilled water systems tend to condense water and you don't want it to rain inside your building. So the good news is if you've measured your pipe, well, you already have linear foot of your insulation. Your air distribution, you'll treat it at the air handler and then we'll move it out through a fan. So here's the air handler that we have on the second floor. You can see we have pipes running into it, and we then have, it's hard to see on the teleprompter, but we have a fan located in this box right here, and we have the duct leading up out of the building, out of the air handler, out to the zones. So inside of there we have heating and cooling coils. For a cooling coil, it could be either water or refrigerant. Your home HVAC is going to be most likely refrigerant, a direct expansion. For your bigger commercial buildings, you're probably going to use water. And we treat it similar to this drawing right here. This is a variable air volume box with a reheat coil. And you can see we take air and we push it across this cooling coil, or this heating coil, as shown here, being red. We move air across it. We transfer heat from the air, from the water to the air, and that's how we heat up the air at this coil. We don't want the two fluids mixing, so that's why we have a heat exchanger there. This is what your coil will look like. Bigger inside your air handler. We then have a fan to motivate the air to move up because air is lazy, so we need to get it out to the zones, and it won't do so on its own. And we move it through ductwork. And then we control the zone, how much airflow at the zone in a variable system with these VAV boxes, or variable air volume boxes, where you can see there's a damper right here which will modulate based on the thermostat whether you're meeting the set point or not, and that'll open and close it. And then we typically return the zone air back to the air handler. One thing you may have, and that's what this picture is right here, this is your package unit, a standard package unit, which contains the whole refrigeration cycle, heating, cooling coils right there. These are very easy to install because you just take them, drop them on a pad, drop them on a roof, and then run ductwork to them. So that's another thing you may see. So our air handling equipment, this is our mechanical room. And we have an animation, supposedly. From inside this mechanical room, we have our air handler right here, highlighted in green. And we have our heating coil and our cooling coil. So we bring the air in. In this case, we're bringing 100% outdoor air into this air handler. We're running it across this heating coil, this cooling coil, and then we are going to, heating coil, cooling coil, and we're then going to push it out to the zones, and we're going to refer to this as our supply air. And inside of there, we have a fan to push it out. I also have noted an outdoor air louver, something you would account for. So our air handler mixes, heats, conditions air. We distribute it with a fan, and you have some options as to what you're going to select from the air handler. We have few options. We have built up. We have our built up, whether it's a package unit or in probably this case inside, you build it inside the mechanical room, each portion of it. You have your different heat sources. Is it going to be a water? Does it have a heating coil? Does it have a cooling coil? Is it going to be a refrigerant, direct expansion? You have package units, so that contains all of that. Do you place that on the rooftop? If it's on the rooftop, we love to call it a rooftop unit because we have no imagination in naming in HVAC. Very descriptive though, so it's a rooftop unit because it's on the roof. And then we have our outdoor pad-mounted package units, which are placed outdoors on a pad on the ground. So this is what it looks like from your RS means. You have on here, you can see all the way over yonder, looking at the wrong monitor over here. We have our air handler with cooling and heating coils, mixing box, filters, and it's listed here as single zone, horizontal, vertical. So what's the orientation of the fan? And we have listed constant volume. So you can have constant volumes or you can have variable volume systems. If you have a variable air volume box, I can tell you it should be a variable volume air handler. And then you have multi-zone down over here, blow-through fan. And then on this other side, we have package indoor units, which can be cooling coils with chilled water or direct expansion, heating coils, which are water, steam, or electric. And then what do we size these on? Once you have the details, these are sized based off of the CFM, your cubic foot per minute of airflow. So that's how much air under design conditions we're going to be pushing through this air handler. So then we can go through, now that we've found our air handler, we can talk about our ductwork. So our ductwork, we take our supply air, we push it out on this main trunk. So this main trunk you can see comes through here, and there's many takeoffs. We're going to focus on this takeoff here. So you'll have to go through and count this for each and every takeoff. So we have our ductwork running through here. Our main trunk is a 44-inch by 42-inch square duct. We are going to take the quantity, we're going to estimate this based off of the weight. It then branches off to a 12-inch diameter stub. So we have a 12-inch diameter stub Y branch right here. So we have a fitting on our ductwork that I could not find a line item for here, so I would include it in your weight measurement for your 44-inch by 42-inch square. So you'd calculate approximately what the weight is of that. We then have 12-inch round duct taken off from here, and this will be measured in linear feet. Our round duct is measured much closer to as we would pipes, so we can have a 12-inch diameter round duct. And we have in here then 4 90-degree elbows, which are located right 1, 2, 3, 4 elbows, and then we have 4 T's, 1, 2, 3, 4 T's, or 3 and then 4 T's located on here, which can be counted individually. So looking in our RS means, things that you'll have to account for. If you are building this up in a high ceiling, you're going to have to account for the cost of building these in a more difficult condition. Above 10 foot, you must add a labor rate adjustment. So you can see here, 10 foot to 15 foot, 6%. All the way to 40 foot high, you're going to have to add 33% to your labor cost. It's going to be more difficult to work on, so you're going to have to account for that. And then we talk about it being sized by weight. So you're going to have to identify the material, aluminum, what is the aluminum alloy, and then how much weight is it. So you'll have to calculate the surface area, find the thickness, find the density of it, and calculate that. That's how you get your rectangular duct. Other things you need to include, are you running a high pressure system? That's going to add more cost to this. You have to be a little bit more careful on how you build it. Higher pressure, you don't want to blow the ducts, break the seals on it. So you're going to have to add to the cost of that based off of the pressure of it. Then your fittings. Your fittings, you're going to have to calculate the weight of your ductwork and the weight of the fittings, and then adjust the overall cost based off of how much percentage-wise are the fittings. So 100% fittings, I believe that says on there 169%. You'll have to add that to your cost. And don't forget your duct tape, an engineer's best friend. Now let's count the equipment in your air distribution. So we have dampers. So leaving the mechanical room, every time you cross a firewall, there's going to be a fire damper. And on here it's indicated by FD. So there's a fire damper located there. And this is 44 inches by 42. We then have dampers located here, or balancing dampers. We have 5 of them on here. Each of these are to then balance out, make sure we have the right airflow going to each of these diffusers. So the way I like to consider it is these dampers, so air distribution is like herding cats down a hallway, but you want so many cats to go into each of your classrooms. So you have to open up the doors by a little bit. So you open the door a little bit, you get a few cats running in there. If you open the door all the way, you'll get a lot more cats running into that classroom. Why do you have cats running into there? I don't know. We like having a fun environment here at AFIT. Then you also have your VAV box located here, and that controls the total airflow to this zone. And this is sized based off of CFM, 1400 CFM. How do I know that it's 1400 CFM? Well, I know how many diffusers we have here. So I can go through and I can count the ceiling diffusers. You're going to check to see what the specifications are of these. These could be 12 inch by 12 inch. It could be 24 inch by 24 inch. There's a lot of different flavors of diffusers out there. So check your schedules to see what they are. And then they list on the drawings, and they usually list in the schedules as well, what the airflow through each of these diffusers are. So if I know I have, what is this, 4 or 5 diffusers, 5 diffusers times 280 CFM ends up 1400 CFM. Somebody with a calculator may be able to call me on my math. All right, we're done, right? No. So at the end of the project, my experience is that what do we like to cut out at the end? The wing commanders yelling at us, turn over the building, the customer's like, we need to use the building now, and at the very end we have testing and balancing. So we need to include our controls. And when we do our cost estimate, we need to include the cost of the controls in here. So our VAV boxes, our variable air volume boxes, are controlled by thermostats. So in each room, you're going to have a thermostat. In every zone, there'll be a thermostat. There's going to be pressure sensors in the duct. We control our variable speed fans based off of static pressure sensors located inside the duct runs. And then we have differential pressure sensors between the supply and return ducts. And this is how we manage the pressurization of the building. And then we have all sorts of temperature sensors in there, our outdoor air, our supply air, our return air, freeze stats that need to be included as well. So you're going to have to find a controls diagram, find these things on there, and then account for them in in your estimate. So testing and balancing, some of your labor-only items that you'll have to add in, they are not included on each of those line items. There's a separate section in RS means. Your balancing valves and dampers, each one costs about $100 to balance. So that one zone will cost $500 to balance out that zone. We then have our variable air volume system, which may cost about $2,000 to go through and balance and test that. Plus then we have each of our VAV boxes. So if you add this up, each line item can very quickly account for a lot. If you don't have this in there and suddenly you get to the end and you haven't budgeted for this, well, you're not going to have system. It's going to be that dull cake without any kind of frosting on there. Will it work? Yeah, but nobody's going to be that happy about it. And you'll get a lot of complaints about it. And then our ducts, we need to insulate them as well. One example that I have was at Al Udeid. We had conditioned air running through a duct in a warehouse, and we were getting a complaint of the roof leaking. Well, upon further inspection, we determined that it was probably because we were condensing water on an uninsulated cold air duct above their office space. Yeah, the quick look was $100 per valve and $100 per damper each, $100 each. So it seems a little high to me, but can add up quickly. So check your RS means. I did a quick sample of there to find out a general cost. But you also want to do it right. So the testing and balancing process ends up being very iterative. You test the system, you take measurements on one valve, you adjust one thing, and then you go check the other valves and you come back to that valve, and then you fiddle with it again until the whole system's in balance. Yeah, feel free to reach out to me. I love talking this stuff. As you can tell, I really like HVAC.